Right, yeah, so hello everyone, good afternoon. Let me toggle the, okay. Yeah, so we missed the previous lecture for the weather, right, conditions. So today I need to kind of shrink two lectures into one lecture. So I combine lecture 4 and 5. And we will be talking about basics of quantum theory, basically, and the aspects that we need for quantum computing. So as usual, let me first import the libraries and discuss what we have learned so far. Right, so first of all, we discussed that in contrast to classical computing, which deals with a bit, right, which is the unit of information, which can be either 0 or 1. For example, in our electronic computer, 0 might be like a low potential, low level, 1 can be higher level in the electronic logic. Right, and all operations basically manipulate with these bits using electronic transistors and so on. And so in quantum computing, we introduce a fundamentally new concept of a qubit, which can exist not only in 0 or 1, it can exist in both of these states simultaneously, okay, with different probability of finding this qubit in state 0 or state 1. And so this fundamental kind of change in using or working with information leads to a drastic change in a computer logic, hardware, and so on. So essentially, quantum computer is something very different to a classical computer. It doesn't mean that a quantum computer will sometime replace a classical computer, because quantum computer outperforms classical computers only in some certain computation problems. Okay, so even when we will have like a powerful enough quantum computer for some particular problems, it doesn't mean that we will watch YouTube using quantum computers or something like that, right? So quantum computers will always be some specific machines to do some specific tasks, okay? Well, saying that a quantum bit or a qubit can be in two states at the same time means that we usually find this qubit in a superposition of two states. Okay. There are other architectures that use like free state qubits. They have another name. It doesn't really matter. What matters is that just like in classical computing, you also can create a computer using, for example, free level voltage states, right? So in quantum, you can also use 3 or 4 possible states, but the simplest one and the most reliable one suggested so far is the one based on qubit, two quantum states. 0 and 1 are basis states, and these constants C0, C1 are complex numbers. They are actually functions of time. They are complex, and the fact that they are complex enables not only superposition, but also constructive and destructive interference of this state. This is something we will discuss more today. So also last time we said that the state of one single qubit can be graphically represented by this block sphere, right? And this concept, this representation works nicely for one qubit, and of course, quantum computer requires thousands and hundreds of thousands qubits. So one cannot use this block sphere representation. People use something else to represent the quantum state of a more bigger quantum system. Yeah, so this is what we discussed so far. And today, let us formulate the main concepts of quantum physics, and I will represent them in the form of postulates. Okay, it's gonna be 6 or 7 postulates. That we're gonna discuss. Okay, so and the first one, we already mentioned this, touched upon probably last time, and let me repeat. So the state of a quantum system, any quantum system, is given by a vector in the complex Hilbert space. Okay, so Hilbert space is a space, there's a vector space of complex vectors. Okay, and the dimension of this space is not restricted to 3 dimensions or something like that, right? Like 3-dimension space is a space in which we live. So Hilbert space is a mathematical space, and its dimension can be up to infinity. So it's not a problem to consider a Hilbert space of a dimension 1000, something like that. Yeah, so this space is represented by a number of eigenvectors which form the basis, right? So these basis vectors 0, 1, 2, and so on. All of these vectors are orthogonal, and their orthogonality allows you to represent this quantum state. Again, this psi is a state of a quantum system given by this vector. Okay, so introducing this basis, you can represent the state by its projection to every single basis vector, right? So this C naught 0 state plus C1 state 1 and so on. Just like the usual vector in 3-dimensional space, we can take Rx, Ry, and Rz, right? So these projections, the components of a vector. So these projections are presented by coefficients C0, C1, and so on. And they are complex because our vector is complex valued. Let us consider an example of a simple quantum system, which kind of represents this statement nicely. So let us have one single particle, elementary particle. It can be, for example, an electron. This electron in quantum mechanics is represented by a de Broglie wave. De Broglie wave. It is essentially a plane wave that is traveling in space, like shown here. Right, this black arrow represents the direction of this propagation, and these red lines give you the front of this wave. Right, and let us assume that this electron meets a single slit in a opaque screen, right? And this is essentially the result of an experiment. The fact that when electron scatters from this slit, it forms the cylindrical wave like shown here, which means that a single electron can propagate in every or in any of these directions, direction 0, 1, 2, and so on. It is actually the infinitely large amount of different directions in space in which the electron can travel. And all of these paths, all of these states are completely possible. Okay, so every single electron can move in any of these directions, and you never can tell which path the electron will move. What can answer this question, in which direction the electron goes, can only give you the experiment. If you measure the electron, then you can tell which direction it moves. But before doing the experiment, you must assume that electron went in all these directions kind of simultaneously. Okay, so this is the example or essence of this summation here. So you sum up over all basis states. Okay, these basis states are orthogonal, of course, because if electron moved this way, it definitely didn't move another way, right? So they are orthogonal in the Hilbert space. Another example of a system with two slits. Okay, so let us use a screen with two slits, two holes, so the electron can move either this way or that way. So the only two options here. Okay, so we kind of restricted the entire Hilbert space of our electron to only two options, path 0 or path 1. Okay, in this case, the psi vector is also represented, is given by two terms, this c sub 0 state 0 plus c sub 1 state 1. And the resulting distribution, kind of the resulting function, the state after these two slits, is given by the superposition of state 0 and state 1. Right. So this is a system with two possible states, and you can already use this system as a simple qubit, right? So it's two quantum states. So it is a qubit. It is a bad qubit, not good, because you hardly can manipulate these C0, C1 coefficients. So it's not a good system to create a quantum computer, but theoretically it's a completely fair system. There are other two-state systems which are more practically useful for quantum. One is, of course, electron spin. You probably know, if not, that's fine. We will be discussing that there are some particles, for example, electron, that in external magnetic field can acquire only two possible orientations. Okay. Before we measure spin in which direction it's oriented, we have to take them into account like simultaneously. We have to assume that the electron is given in both states simultaneously, but we can do the measurement, we can measure the spin, and in half % of the time, we will find the electron up, directed upwards, other 50% it will be downward directed, and no other possible direction. So only two options here. Just like in electromagnetic wave, you know that electromagnetic wave, if it's a plane wave in free space or in a waveguide, like in an optical fiber, it can get only two polarizations, okay, like vertical and horizontal polarization. Again, before doing the measurement, you have to take into account the both of these states. But if you measure, you can find that every single particular photon will be oriented either in the upper, in the vertical or horizontal direction. And the last example, which is schematically presented here, it's kind of an atom. It can be natural atom or artificial atom. And well, so any atom is a system with discrete electron energy levels, right? And we can always select just two of them and consider transitions between just two energy levels. So the lower level will be named ground level or zero state. The upper level will be state one, excited state. And considering these transitions between the two, you can describe the behavior of a qubit. All right, do you have any questions regarding this postulate one?
No.
Yeah, still it's pretty important kind of understand the meaning of this statement. So what is a quantum state, right? So here we're starting from a state of a quantum system without explaining what is a state of a quantum system. So the actual answer is that we don't know what is a state, the quantum state, because it is something new that we have never observed in around us in real life. We cannot compare this with any kind of mechanical abstractions, mechanical models like those masses on a spring or pendulums or some clouds. Okay, so the electron, for example, in an atom is not a particle, is not a ball rotating around nuclei. it is not a cloud because we always detect electron like localized in one point. Okay, but before we detect it, it's spread somehow in the form of kind of a cloud, but it's not a cloud. So the point is that since we are classical, right, we work in a classical way, and our world is a classical world. We don't know how to imagine this quantum state. And the best we can do, just assume that it is some sort of a state, okay? And then represent the state by a vector in a Hilbert space. This is the situation. If you ever watch these kind of lectures about intro lectures about quantum physics, quantum mechanics, people usually start with this statement that it's not possible to understand how it works. But this is the reality, because quantum theory predicts the results of experiments with overwhelming accuracy. Okay, so it's the most accurate theory that predicts some experiments with the greatest accuracy, and also proven in thousands and thousands of experiments. So yeah, very, very interesting. So state of a quantum system is given by a vector in the Hilbert space. And we truncate this space to a two-dimensional when we work with a qubit. Which brings us to the postulate 2. Okay, so we say that, okay, the vector in the Hilbert space gets some projections on the basis vectors. And what is the physical meaning of these projections? Okay, and the physical meaning of these projections is given by the rules called Born's rule. So Born was the greatest physicist, and he bring this connection between the math and the experiment here. So he said that these coefficients Cn represent the probability amplitudes of finding a quantum system in a particular state, n here. So, okay, so it's a probability amplitudes, not the probabilities, but probability amplitudes. So what it means? It means let us return to this picture here. So I observe the electron that is diffracted on a single slit, and it can go different ways, right? And I can put several detectors around here and send the electron like one by one. And after kind of 1,000 experiments, I will find some portion of electrons coming here, another portion here. So maybe more electrons will arrive to this point because it's kind of more symmetric point, right? And so on. So, and then I can plot the kind of distribution of electrons after this slit. It will be some kind of a function with several minima and maxima. Okay, so this distribution, the final distribution, is given by the absolute value squared of this coefficient Cn. Okay, But the coefficient Cn itself is a complex valued thing. So it contains not only amplitude, but also a phase. And this phase allows these states to interfere, basically to form this maxima and minima, For example, here, okay, so electron in the double slit experiment can go through the upper slit or lower slit with different probability, okay? And then the combination of the two, of their superposition of the two, leads to this function, okay? But the measuring through which slit the electron goes through is given by the absolute value squared. Okay, so this is the Bohr's rule principle. The probability of the concrete result of an experiment is given by the absolute value squared of this projection of the quantum state on a particular basis vector. Do you have any questions regarding this part? Okay, if not, then postulate number 3. Physical observables are represented by Hermitian operators. Okay, so this statement might be completely meaningless for you for now because we didn't discuss what is physical observables, what is operators. Well, we discussed operators, but very quickly. And you, of course, or you probably don't know what is Hermitian, right? So let us discuss these points one by one. So first of all, observables. It's very simple. Observables are physical quantities that we can observe or detect, measure in experiment. Okay, like typical examples of observables could be position. I detected electron here or here, so it's a coordinate, right? A coordinate is observable. Momentum is another observable. I can measure momentum in experiment. Also spin, up or down, it's also measurable. It's also observable. And of course, since we observe, we measure these quantities, their values must be real. Okay, so real valued. We never measure complex valued numbers in experiment, only real values. And mathematically, these quantities with real values are represented by Hermitian operators. Okay, so a few words about operators. Operators are mathematical operations that from one function or a vector create another function or another vector. It's like simply speaking, right? Here I put more rigorous mathematical definition, but operator is nothing but doing something with a vector or a function and obtaining another vector or another function. In quantum, we're particularly interested in linear operators, and linear operators are given by this definition. So if I have operator, by the way, operator is usually or sometimes is given by this bolded letter with a hat. on top. Right, so what is written here, I have operator which acts on a composition of two vectors, right? One vector multiplied by some constant plus another constant multiplied by another vector. And this simply means that the result of this action is given by the sum of the two, and you can take the constant out from the operator. Several examples. One can be differential operator, right? Like this coordinate derivative, right? Derivative, of course, leaves the constant alone. You can take the constant from the derivative, right? And of course, this is a linear operator because derivative of sum of two functions equal to the sum of two derivatives. Similarly, integral operators, like shown here, with some kernel, right? This k kernel multiplied by this function. If you integrate this integral, you will of course get another function, which will be the function of x. So it will be another function. You produced function from another function using this operator. Right. So what is more important here is that operators can be represented by matrices. Okay. So again, if you have a vector like this quantum state in the Hilbert space, you can apply operator to cause this vector to change the orientation, change the direction. You can rotate this vector. And this operation will be given by some sort of a matrix. Okay, so matrix acting on a vector will generate another vector in the same Hilbert space. And for example, here I put this simple example. So let us consider a vector with components 1 and 0, and then you can create this matrix A. For consistency, let us change it to O. And then applying this operator O on a vector V, we will transform this vector to another vector with another components. Okay, changing these elements of the matrix will change the components of the vector. So using this operator matrices, you change vectors. So here what I do, I take this vector, then I apply an operator, some sort of operator, again, change this vector to another transformed vector, and then plot the result to show you graphically what actually happens, right? So suppose you start from this red vector V with components 1 and 0, so it's vector directed along X, right? And then you apply this matrix, and it generates a new vector, this blue vector with new components. Of course, you can change this vector, this matrix. You will get another result. For example, this matrix, this identity matrix 1, 1, right, generates simply the same vector, and so on. Some operators we already discussed last time. I took this part from our previous lecture. For example, Pauli matrices, Pauli operators, they represent some kind of operators, right? They can do some operations with vectors. So let us write down these matrices because we will use them. Sigma x, sigma y, sigma z. Let me double check. 0, 0, 1, 1. 0, 0 minus I. Yeah. When we talk about operators, very important concept is eigenstates and eigenvalues, or eigenvectors and eigenvalues of operators. So what is eigenvectors and eigenvalues? An eigenvector of a matrix is a vector that doesn't change its orientation after applying this operator on this vector. Okay, so for example, let's consider picture here. First, vector v1, vector v1. If I apply operator a on this vector, I create another vector a v1, which is changed in amplitude and orientation, magnitude and orientation. So this vector v1 is not eigenvector of this matrix A. However, I can always find a vector like v2, shown here, which changes only its magnitude upon applying this operator A. So operator A applying this vector is equal to some constant times this vector. This constant simply changes the magnitude of this vector. So this is eigenvector. So any eigenvector, and by the way, the corresponding constant by which the vector changes its magnitude is equal to, or is named eigenvalue. And in order to find the operators eigenstates and eigenvalues, what you just need to solve this equation. Fortunately, in Python, we have a very nice function. Specifically in NumPy, we have this function linalg.eig, okay, eigen. So this function allows to find the eigenstates and eigenvalues like automatically. So let us consider matrix A, some arbitrary matrix, and this function returns two arrays. Okay, so the array of eigenvalues and array of eigenvectors. Let us run this. Why just one? No, I need all. Okay. So the first one is eigenvalues. Okay. So there are two eigenvalues and two eigenvectors. So every column in this array is a vector. So two eigenvectors. So a matrix with 2 by 2 has two eigenvalues, two eigenvectors. Then a matrix with components like 3 by 3 or 4 by 4 would have 3 eigenvalues and 3 vectors and so on. Yeah, let us check that these are actually eigenstates and eigenvectors and eigenvalues. So what I do, I need to first take the first element in this array, which is the first eigenvalue, right? Then I take the first eigenvector here, the first column, and the first element in eigenvalues, and then I simply check this. So I take the product of the matrix by vector, and then the product of the eigenvector and eigenvalue to check they are the same. So they are indeed the same. The same thing probably I can check if I check if they are identical, right? False, false. Why? Because I guess they differ by a small value, right? Up to the computation error. Okay, so they are identical. Yeah, let us find the eigenstates, eigenvalues of the Pauli matrix Y, for example. I need this one. So I basically do the same sigma x, for example. Right. So these are eigenvalues and eigenvectors of Pauli matrix X. This is matrix Y. And finally, this is matrix Z. So you notice that the eigenvalues of all the Pauli matrices are the same, 1 minus 1. But the eigenvectors are different. So these eigenvalues is nothing but these two orientation of spin. So for example, sigma Z eigenvalues give you one for upward direction, minus one for downward direction. And eigenvectors are the states that this particle acquires in each of these states. Okay, so you can summarize the states, the eigenvalues and eigenstates of Pauli matrices in such a table. So it's very important to kind of remember this table because essentially these three types of states form the block sphere. Okay, so the state plus, state minus, and so on. We will discuss them next week. Today, yeah, we continue the what's called the postulate, and the last one we need to discuss is Hermitian operators, right? What are Hermitian operators? Hermitian operators are operators that coincide with their conjugate transpose version. Okay, so you see this operator H, and then this dagger symbol. So this dagger symbol sum up two operations: the complex conjugation, denoted by the star, and then transposition, when you change the rows by columns and vice versa. Right, so after this transition and complex conjugation, Hermitian matrix coincide with itself. So for example, consider this one, and whether this matrix is Hermitian. So it gets real values on the diagonal, so they don't change after complex conjugation. The off-diagonal elements are imaginary value. They change the sign upon complex conjugation, but then after transposition, the matrix indeed returns to its original form. So this matrix is Hermitian matrix. Let us check that. So I write this matrix here, and then you can apply the dot t, which is the method for transposition. We discussed that probably last time, right? And conjugation for this matrix. And then I do minus the same matrix, so the result will be the I matrix, the zero matrix. Indeed, the result is the zero matrix. Probably when we discussed the complex conjugation, we used numpy, right? Numpy dot conjugation, something like this, yeah. So zero matrix, is it really zero matrix? We can check if they coincide. Okay, yeah, now it works, true. So every single element in these two matrices coincide. So Hermitian matrix doesn't change upon dagger operation, complex conjugation plus transposition. Why it's so important? It's very important actually, specifically for quantum, for two reasons. First is the fact that the eigenvectors of a Hermitian matrix are orthogonal and form the basis of in our space, in our complex valued space. Okay, so you can use eigenvectors of a Hermitian matrix as a basis to describe the quantum system. Okay, this is first. They are orthogonal. And the second one is that eigenvalues of Hermitian matrix are real valued. So real valued, it means that we can use them to represent observables. Right here, we said that observables must be real valued because this is what we measure in experiment. It means that observables can be given, represented by Hermitian operators. All right, what I do here, yeah, for this Hermitian matrix, we define that this matrix is Hermitian. I can check that the eigenvalues indeed real valued, which means the imaginary part is equal to 0, right? So it's true. And then, yeah, and then doing the dot product, right? So in order to check that the eigenvalues are orthogonal, I need to take the dot product of the vectors, of the two vectors, to check that they indeed orthogonal. So what I do MP, right, then dot product, then the vector, the first column, and then the second column. And also I have to take into account that these vectors are complex valued. So I need to NP conjugation. I need to complex conjugate the first vector. Yeah, so the result is 0. So indeed, these vectors are orthogonal. If I change this matrix somehow, for example, do 2 here. Okay, so now this matrix won't be Hermitian. We see false, false, and this product most likely will be so it's something else. So this vector is not orthogonal. Only Hermitian matrices have orthogonal eigenvectors. That's why it's so important for quantum. And also their eigenvalues are real values. So yeah, postulate 3 physical observables are represented by Hermitian operators, what we just discussed. One particularly important type of operators is called Hamiltonian. Okay, so many words today, but yeah, you will use to them. Hamiltonians. So Hamiltonian, what is a Hamiltonian? Hamiltonian is simply operator of a total energy. Okay, so when you describe the system, you find the total energy. So this operator represents the total energy of your quantum system. So this operator represents total energy. What it means? It means that this operator, of course, gets its own eigenvectors and eigenvalues. So every eigenvalue gives you the exact level of energy, amount of energy in your system. Amount of energy in your system. You probably are aware of this formula. If not, that's fine. So it's a Hamiltonian for a particle in a potential V. Okay, so it's a kinetic energy. This is potential energy. In classical physics, the formula looks the same up to this hat, right? On the operators. An example, let us consider a hydrogen atom. Okay, hydrogen atom gets a proton as a nuclei and an electron that orbits the proton, right? For this system, you can write the Hamiltonian. It will be kinetic energy of electron plus the Coulomb interaction energy between positively charged proton and negatively charged electron, right? The attraction force. So for this Hamiltonian, you can write the equation for its eigenstates and eigenvalues. And then solving this equation, you will find the solution for different state of the electron and for different orbitals in the system. So the solution, even for simplest atom, which is a hydrogen atom, even for such a simplest atom, the solution is quite bulky, and the possible states of electron quite complex. But they are very well agreed. The solution is very well agreed with the results of experiment. Okay, so for example, the transitions of electron from higher state to lower state, of course, accompanied with the emission of a photon from the system, like shown here, and these transitions, we observed them in experiments. People gave them different names according to the researchers who observed and investigated these lines. Okay, so these experimental results, quite complex results, because there are a lot of energy levels here and possible transitions, coincide with extremely high accuracy with the quite complex theoretical result. Today we have not only hydrogen but also helium, right, which is 2 proton, 2 electron states, this like theory, rigorous theory, but not for the others, because it is an example of a mathematical problem with non-polynomial complexity, right? So adding more particles leads to increase in complexity of this problem, like exponentially. And one of the reasons why we need quantum computers, because then we would be able to check the quantum theory on other atoms, right? So even a hydrogen atom gets several energy levels in its spectrum. You can always restrict your consideration to just 2 of them. Okay, in this case, if you work only in the frequency spectrum that coincide with this particular transition, then the system will behave just as a qubit. Quantum system with 2 quantum states, and then the general state of this qubit will be given by this superposition principle, and the Hamiltonian in the energy representation, meaning that the energy on the energy operator is diagonalized, right? So the diagonal elements simply the energy states of energy levels of this of these states. All right. Postulate 4, measurements, and specifically projective measurements. So we said that in general, a quantum system is presented in a superposition of quantum states. What happens when we measure this system? Okay, so as a result of a measurement, we can get only one of the possible eigenvalues of the observable operator. Like here, for example, there are many different energy levels, but when we measure the system, we will always find the electron in one of these energy states, and not somewhere like between. Only these possible states will manifest themselves in an experiment. Okay, so only one of the possible eigenvalues of the corresponding operator of the observable will show up in experiment. What happens to the function? Because before experiment, the function is in the superposition of 2 states, but after measurement, we can get one of these, either one state, but not the 2 together, right? It's only one. So what happens, obviously, is that the wave function somehow collapses to one possible state. and you never predict with certainty which one state will show up. You can tell only the probability of this experiment. Let's say the state CA, the state A will show up in 70% of results, and state B will show up in other 30% cases. And then, yeah, this will be given by the different coefficients, CA, CB. So the measurement leads to the state vector to collapse to one of the possible eigenvectors. Only one possible eigenvectors. And as we discussed, the probability, which one, will be given by the Born's rule, the square root of the magnitude of the coefficients C. Theoretically, this process is presented given by projection operators. So projection operator is simply the out product of the corresponding particular vector. Okay, so this is the state vector I, which represents one of the eigenvectors, and you form the outer product of the two, and this is the projection vector. If you now apply this projection operator, if you apply this projection operator on a general state O, right, it is expressed in this way. So this is the projection operator, this is the state O. Then now you can notice that this product is nothing but inner product of the basis vector and the state vector, which is simply the projection of the state vector on the particular basis vector Cm, right? So this is the result. So indeed, this projection operator creates the particular state M from the general state, which is the superposition of all possible states, right? And it gets a property that if you apply this projection operator twice, it's simply equal to the projection operator itself. Again, it's straightforward to show that. You write the square of this operator, then operator times operator. Then, since these basis vectors, basis states are orthonormal, right? Which means they are orthogonal and normalized, so they have the length 1. It means that the basis vector times basis vector is equal to 1, right? And as a result, you get this outer product, which is the projection vector itself. Do you have any questions? Awesome. Then we converging. Yeah, we have only 2 points to discuss. Point number 1 is a postulate 5. So, as we just discussed, the observables are presented by Hermitian operators, and we can observe, we can detect their eigenvalues in experiment. But of course, any system has different types of observables, right? I can measure energy of an electron, I can measure momentum, coordinate, I can measure spin of the electron, and so on. So different observables. And not all of them are or can be measurable, simultaneously in the same experiment. Okay, like for example, coordinate of an electron. In order to measure coordinate of an electron, I have to stop electron in some point in space, right? Or at least affect this trajectory of the electron, which unavoidably will change the momentum of the electron, right? So these two cannot be measured in the same experiment. And the question whether or not two two observables can be measured in experiment is given by the appurator, which is called commutator. Okay, this commutator is denoted by these rectangular parentheses, brackets. So it's nothing but the difference between the product of two appurators taking into these two different ways, AB minus BA. So when this appurator, this commutator is 0, in this case, the appurators can be these observables, observable A and observable B, can be measured in the same experiment. Yeah, so the commutator equal to 0. If commutator is equal to 0, we also say that these two operators commute, right? And if they commute, they can be diagonalized simultaneously. Okay, so this basically means that we can find we can measure their eigenvalues in the same experiment. Some examples of commutative operators. One example is the coordinate. Of course, if I measure coordinate x, of course I can measure coordinate y, and their operators, which is simply x and y, doesn't change it when I change their product. Identity operator, of course, commute with any operator, even though identity operator doesn't represent any observable. Also, momentum operator and another coordinate commute because momentum operator is given by this x derivative, and it doesn't apply to y, so it doesn't change y. You can treat y as a constant and take out from the derivative, right? So you can exchange their positions. And spin, yeah, so this is trivial. Any operator commutes with itself. However, if the commutator is not equal to 0, then these two observables cannot be measured in the same experiment. And one example, for example, is the spin operator, so Pauli operators x and y. So as we said, Pauli matrix represents the experiment of measuring the spin orientation in a particular direction, which is given by the direction of applied magnetic field. Okay, so it means that if I measure spin, the orientation in one direction, of course, it makes impossible to measure this orientation in another direction. So these two matrices must not commute, and indeed the result is given by the third Pauli matrix. So let us check that. So I do commutator and then sigma x matrix times sigma z minus sigma z times sigma x, and the result is this one, 2i times sigma y. All right. Do you have any questions about commutators and when two observables can be measured simultaneously? All right. And I guess the final, the final postulate, number 6, is a statement that time evolution of any quantum system is given by unitary operator. Okay, so it's another type of very important operators for quantum. One is Hermitian operator, which represents the observable things. And now we need to discuss unitary operators. So unitary operator is an operator that satisfies this criteria, right? So it's basically, if you take the operator dagger, you multiply it by operator itself, the result is identity operator. Equivalently, if you multiply this equation from the right by inverse operator u minus 1, right, you will get this result. So the dagger applied to unitary operator is equivalent to the to reversed operator, inverse operator. So what it means and why it's so important. So you know that, so if operator is represents some sort of a transformation, some kind of rotation of a state vector, for example, right? The opposite, the reversed operation, is given by the inverse matrix u minus 1, right? And the fact that this inverse operator, which restores the system back to its original state, equals to the operator dagger, means that this operation is time reversible. Okay, why time reversible? Simply speaking, it's because this complex conjugation reverses the physical process in time. Like, remember, for example, like a wave, e to the power of I omega t, right? If you make the complex conjugation, it will be minus I omega t. So equivalently, it's kind of the same process, but reversed in time. And transpose also means reversion in space, kind of in direction. So all of this simply means that unitary operator represents operation that can be considered in either direction, in one direction in space and time, and in other direction space and time. It can be reversed. Okay, so in quantum, any operation is given by, I mean, not any, but the vast majority of quantum computations are based on unitary operators. Okay, so basically if you have a circuit, quantum circuit, we will discuss that next time, of course, just for understanding. So if you have a circuit, it means that you have different unitary operators there, and you have input and output. So the fact that these operations are reversible means that you can run this circuit from left to right and from right to left, and you will get you will restore the original state. You will come to the original state, to the initial state. Yeah, so this is the importance of unitary operators in general. Is not only for quantum, like in communications, in other areas. The unitary operators describe operations that can be reversible in time. Specifically for quantum, any quantum system is governed by Schrödinger equation, right? I'm bringing the Schrödinger equation here just for you to look at it. Once we won't really use it, of course, but I have to, because it is the most important equation in quantum physics, basically. So what it takes, it includes the state vector, right? So this is the state vector in some moment t. Then it connects this state vector in some moment t to another time moment through this time derivative, right? So time derivative means that you jump to another point, to another time instant, and this operation is given by this Schrödinger, this Hamiltonian. Okay, so this H operator is Hamiltonian, the operator of the total energy. Okay, so if you know for a given system, if you know the Hamiltonian, which is the total energy, you can write down this Schrödinger equation, solve it, for example, numerically, and find the state vector in any time moment ever. So you will get the time evolution of your system in time. This Schrödinger equation can be rewritten in an operator way. Okay. To do so, let us notice that we take the time derivative of this function and then get the same function times or being applied to or changed by the operator Hamiltonian, right? So it's a time derivative of function equals to function, which means that we can rewrite this equation using the exponential function. Okay, like formally rewrite this equation using exponential function. So if we write the state vector as a product of some operator u times the initial state vector in some initial time moment, right? Then if you take the time derivative of this expression and multiply by I and h, you will get exactly this. If this operator u is given by this formula here. So it's a operator u is equal to exponential function to the power of this minus I over h, then Hamiltonian times t. So it's a this is the operator in an exponential form. Okay, so these two equations is nothing but the Schrödinger equation, just rewritten in a different way. Okay, from these two equations you can restore the Schrödinger equation easily. So it's a Schrödinger equation written in an operator way. So if you solve the system, you starting from some initial time instant, then you apply your operator u to jump to another moment in time, then another moment in time, and so on. So you can trace this evolution of the system applying this operator u. And since operator h is Hermitian, you can easily check that this operator is unitary. So it's a unitary operator. All this simply means that you can describe evolution of any quantum system applying unitary operators. Importance of unitary operators, yeah, something that I already said. The unitary operators are time reversed. They also keep the probabilities unchanged. So they preserve all probabilities, which means that these unitary operators, they don't change the well, they basically they describe the evolution of a quantum system in a best way. They don't bring something extra and artificial to the analysis, because these probabilities, as we discussed, probabilities what we observe in experiment. So our mathematical approach analysis must leave these quantities unchanged, right? And very important is that all quantum gates, at least those quantum gates that we will cover in our course, are all given by unitary matrices and unitary operators. Two examples I show here. So this Pauli matrices, they not only Hermitian but also unitary. We can also check this fact by testing this, right? So you can take the or this. Yeah, you can take the dagger and then multiply by this matrix and check if the result is identity matrix, right? So conjugate transpose times the matrix itself gives you the identity matrix, right? The same you can check how to write this numpy 0. No, it's not 0. Identity matrix on that side. yeah, it's easily seen that these matrices are identity matrices. And final example is the Hadamard operator. Another operator which is very important in quantum. We can actually box this formula because it's quite important operator. We will see that this operator or this gate creates a perfect quantum superposition of a single qubit. But for now, let us check that this operator is unitary, right? The fact that it's Hermitian, it's clearly seen, right? So all elements are real values, and the off-diagonal elements are same, so it doesn't change upon complex conjugation and transpose. But whether this operator is unitary, so again, we test this unitary the same way and get identity matrix. So this operator is unitary, and so this dagger operation, which is conjugation and time and transposition, used quite often. So instead of applying these two operations, you can use just one, get H. Okay, so it's getting dagger or getting Hermitian conjugation. Okay, so it's the same thing, but up to the numerical up to the numerical accuracy. Okay, so if you for example round, right? So called round this guy, you will get 0. So it's a unit identity matrix. All right, so it's all for today, perfectly in time. Let me stop the recording and then we can discuss quickly if you have any questions.